So, welcome everybody to the April meeting of the Tucson Amateur Astronomy's Fundamentals Group. Uh, this tonight, we have two presentations. One from Pete Hermes on the astronomer Henry Russell, who was one of the two figures behind the Hertzsprung-Russell diagram. And we will get a little bit more info on this figure. After that, I will be representing a presentation I gave in 2017 with some updates on black holes and some of their fundamental properties. Pete, whenever you are ready, go ahead and take the share.
Okay.
After I make you co-host.
That's right. I just saw that.
There you go.
Let's try that again. Oh, there we go. I would like this one. Share. Okay. So I want to make sure everyone should be able to see my first slide. If I get a thumbs up from Doug. Good, thank you. Okay, good evening. As always, a pleasure to present before you all. Tonight's topic that I worked on is Henry Norris Russell. Russell is probably one of the more preeminent contributing astronomers of the 20th century. Uh, there were a number of them, but as far as especially moving in, he was born in the latter parts of the 19th century, but most of his work, of course, was in the 20th century, his education. And moving into that period, we now see, we see a little bit more with respect to astronomy becoming more of a firmer science, I guess is the best way to look at it. And certainly that's something that's for discussion. But principally, Russell was an astronomer, but he had a very, very strong background in mathematics and math. And that'll be explained a little bit. And also, he was a very religious individual. He didn't see a conflict between science and religion. And I don't know, in looking at some of his philosophies, there were generally some philosophers he followed, whether or not it was more or less. I think, if anything, he tried to see a conjunction or a marriage between the two disciplines, and not so much conflict. Not that one necessarily explained the other, but he had no issues with that. Although I think he was a very devout religious person for a good part of his life. But anyhow, moving on into the presentation. So, as usual, I'll take a look a little bit at his life, education, work, legacy, and of course, references. This will not be an exceedingly long presentation. I'm not going to bore you with a lot of details and minutiae, but of course, as we move into some of these astronomers in the 20th century, there is a lot more information available because a lot more was written down, and certainly there are a number of references on Henry Russell and make note of some of his work and some of the things he did. But needless to say, he was born in 1877 in Oyster Bay, New York. For those of you that aren't familiar, Oyster Bay is basically out on Long Island. Oh, probably just a little bit east of what would be, what is that, Queens area, or, just out onto the island on the north side. Uh, During his presidency and maybe preceding, Teddy Roosevelt had a pretty big mansion. I guess mansion is the best thing to call it. I actually toured the thing a few years ago. It's kind of interesting. But he had a house out on Long Island in the same area, Oyster Bay, and he was probably one of the people that made Oyster Bay rather renowned and famous. Uh, Russell's parents were the Reverend Alexander Gatherer Russell, Presbyterian minister, very liberal, and his mother, this is what I hate when I put that down there, Eliza Oxy Norris. Interesting thing about her mother, I mean, of course, here you're going to see, you see the formation, the bases that really established a foundation for Russell's life. He was, his father was a minister, so this led to him becoming probably devoutly religious, and it continued on through his life. So it was something he did accept. And his mother actually, and to include her mother, had math backgrounds. Not that they were formally educated necessarily, but they were very adept, as the way the description was put in. So certainly this gives a lot of credence to some of the basic foundation of Russell's life. He was the first of three sons born to Alexander and Eliza. And kind of interesting, I mentioned this because, the parents showed him a transit of Venus across the sun when he was only 5 years old. Something that I think, Russell was able to understand to a certain degree. He was, I mean, later on, you'll see, basically, I think he was a borderline genius. Whether or not that was apparent at a very young age, I don't know. I know most assuredly he probably was by the time he finished his first undergrad degree. He was married for quite a long time to Lucy May Cole. They had four children. Incidentally, one of his daughter might have been his only daughter, uh, who lived almost to the year 2000, married an astronomer by the name of Frank Edmondson, who was an observing assistant to Tombaugh at Lowell Observatory. And of course, we know Tombaugh is the discoverer of Pluto. And he passed away in February of 57 and was actually buried in the Princeton Cemetery. Russell has very extensive and long ties to Princeton, as we'll see when we go through the presentation here. His education, he graduated from Princeton Preparatory School, so they were in the area in 1893, which would be, from what I understand, tantamount to finishing basically high school, and then obtained his Bachelor of Arts from Princeton University, having studied astronomy. Note, he's only 19 years of age when he finishes his undergrad degree. And he graduated with honors, not just regular honors, but this is something you don't see too much, insignia cum laude. Insignia is remarkable. Cum laude is with praise. You'll see magna, you see summa. This is a little bit of a degree above it. He was very um, well thought of by the faculty at Princeton. They recognized him as being an exceedingly bright individual. I suspect not only just in his area of expertise, but other areas too. Russell, throughout the years after he graduated, he had advanced studies at Princeton, but primarily based on his undergraduate degree. He frequently attended reunions of his undergrad class and was very instrumental in as far as helping form these, and also very knowledgeable of the class. His favorite study was math. Sport was mountain climbing. He was very good at math, and that explains some of how he accomplished some of his work in astronomy in his professional life. He did obtain his doctorate in 1900, studied under Charles Young, a noted astronomer who was, I believe, also may have been the director of the Princeton Observatory. But Young's expertise was principally in solar spectroscopy, something that you'll see here again later on with respect to Russell's um, area of study. His thesis was an analysis of the way that Mars perturbs the orbit of Eros, and he was granted, when he got his degree, also attained with summa cum laude honors. So not surprising. I guess he took a step down when he finished his doctorate. I don't know. And by all means, if anybody has any questions, please don't hesitate to pipe in during the presentation. Like I say, it won't be that long, and I don't mind someone else talking in the middle of this also. When we move to astronomy, as far as his working profession, he was a researcher. After obtaining his doctorate, he was a research assistant attached to the Carnegie Institute over in Cambridge, and worked with Arthur Hanks, determining the astronomical unit, the length of the astronomical unit, and under the strong influence of George Darwin, also working in developing some of the first photographic parallax programs to measure stellar distances. And this was essentially, for all practical purposes, his postdoc work that was accomplished at Cambridge. Shortly thereafter, after 2 years, he returns back to Princeton and becomes an astronomy instructor. And for the most part, he is at Princeton the rest of his professional life, all the way through. One of the reasons why he was buried in the Princeton cemetery, why he is so attached to the school, both professionally and academically. He's becomes an assistant professor 3 years after he's an instructor, and a full professor by 1911. So he's worked at Princeton all of 6 years at this point. As far as whether or not it was a tenured position, I suspect it was, and uh, I don't doubt that not that his advancement was necessarily accelerated, but I don't doubt that it was, given his propensity for the understanding of the two areas. Basically, Russell was one of the first ones to develop I guess, astrophysics as a discipline, not just astronomy, not just physics, but actually marrying them up. And you'll see something else a little bit later on. I'm sure he did observations, he collected data, but a lot of his work, a lot of what he was interested in is basically taking that data and trying to solve problems with it, taking and marrying it up with theory and trying to work those two together. Anyhow, he did become director of the observatory of the Princeton Observatory in 1927 and had a long tenure with that and some of the programs that were done. He wasn't just at Princeton, too. As you'll see later on, he traveled quite regularly out to Mount Wilson in California to work with astronomers out there, not necessarily doing observations, but trying to, get to know them, establishing relationships, collaborations, and using some of their data and some of their observations. Of course, one of the principal things that Russell is responsible for, along with as our Hertzsprung, was developing the Hertzsprung-Russell diagram in 1910 that basically, and I'll get into a little bit, I've got a little brief summary. I'm not going to get into a lot of detail, but it explains some of the basic characteristics and qualities of stars, for the most part, describing all of them. And later on, he also helped develop the Russell-Sanders coupling, LS coupling, with Frederick Sanders in 1923. Those were probably two of his more notable early works. All in all, I think you'll see at one point he published in excess of 200 papers during his career. Not all of them dealt necessarily with astrophysics, astronomy, or physics. Sometimes I think he had a couple of papers that actually delved into religious areas and philosophical areas too. But in taking a look at the Hertzsprung-Russell diagram, basically showing the relationship between a star's intrinsic brightness and spectral type, and also presented a theory on stellar evolution. And this is the bulk of what Russell did early on in his career and probably continued thereafter. Is it a perfect example? No, but it's probably the best that we have at this point. But basically associating the star's absolute magnitude with its different spectral types and actually showing a little bit of the stellar evolution along the way. Russell made, physics the core of astrophysical practice. Here again, not just doing astronomical observations, but actually trying to work on theories, trying to work out problems with the data and the observations that was being collected by a lot of his colleagues all around the country, both on the East Coast, at Princeton. Like I say, he frequently made trips out to Mount Wilson, California. He wrote one of the definitive texts along with two other gentlemen that was used for a couple of decades at the college level with respect to astronomy. And one thing too, a couple of months ago, I did a presentation on Cecilia Payne-Gaposchkin. And it was kind of interesting because there was one little bit in there, and it was probably, I don't know if it was necessarily a black mark. Everyone makes mistakes. Astronomy was a developing theory, but certainly Gaposchkin was one who also worked in stellar composition and evolution to a certain extent, and had proposed in her thesis, in her graduate thesis, that the sun was different from the Earth in composition. It was primarily hydrogen and helium. Sure, some of those very components are present in the Earth, but not in the same proportions. And basically, her modeling stellar evolution, which was much more accurate, was something that at the time of that writing, that Russell was one to cite that didn't agree with it. However, few years later, he did come to find through independent research and through his own work that Gaposchkin's basic theory of stellar composition was correct and was accurate. Unfortunately, he never really, and it's not a matter of apology, but he never gave her credit, the credit that was due her, which was typical of a lot of female scientists that worked in the field, if not other fields, I'm sure, but especially in astronomy and physics. And it's something that, it didn't really hurt her career that much, but it certainly didn't help it. And, I consider it a little bit of a black mark on Russell's that he didn't fully, try to make it right and identify and give her the proper respect for the work that she had done. Uh, like I said, when he returned, even from the onset of returning as an instructor at Princeton in 1905, he didn't look at astronomy as merely collecting data and doing observations, but rather a problem-oriented research that, basically married theory and observations, putting the two together, trying to use the observations and data collection to identify and provide information with respect to some of the theories, some of the problems that he had put together, particularly, the Hertzsprung-Russell diagram and the, how, the qualities of stars could be related. He was able to explore new problems and apply his math talents under Young and Lovett at Princeton during his grad work. And of course, it was very much recognized. Research was his chief activity. Yes, he was a professor. Uh, I got the impression from the research that I conducted, and he was, like I say, director of Princeton's observatory for 2 decades. But he had a tendency to sort of let those things off to others, whether or not it was the assistant director of the observatory and grad students with respect to taking care of his classes and taking care of the students. I suspect that was probably the case. Not that he totally ignored it, but he spent most of his time in research, realizing that he certainly had others around to take care of these other duties for him. You can see a couple of his notable students. They both, all three of these gentlemen became directors. And oh God, I'm sorry, I misspelled Harvard and Donald Menzel's line there. But with respect to become directors of either the Harvard or Princeton Observatory. For the most part, up through the 1920s, his research focused on planetary and stellar astronomy and astrophysics. One of the things that Russell worked on was an analysis of binary star orbits, calculating, in other words, coming up with ideas about calculating the masses and dimensions of eclipsing variables were some of the first examples he used, and also developing methods for determining distances, motions, and masses of the binary stars. Elgo's probably a great example and maybe a well-known example of an eclipsing binary where you see you have a smaller dimmer. I'm sorry, you have a smaller dimmer star. Of course, this only works when the plane of rotation or the plane of orbit basically is in line with the Earth. In other words, we're not looking at them at 90 degrees. One star will pass in front of the other and behind the other occasionally, and you're going to see these two changes. You see the graph over there, which is basically the change in the luminosity or the light. Big change, a big dip in luminosity when the smaller star, which is generally not going to be as bright and not as luminous as its parent star, drops down that light. And then a minor change in luminosity when the combined luminosities of those two stars side by side will decrease slightly when the smaller star passes behind its parent. Anyhow, here again, make the point. Russell's strength was in analysis and managing data. Yes, he did observations. He did data collection, but that wasn't his principal work. And here again, for almost 20 years, he spent quite a bit of time at Mount Wilson. Here again, working with those astronomers, taking a look at their data, taking a look at their observations, and trying to address some of the problems in astronomy as it became, or in astrophysics as it became more of a, I like to say detailed science. This is where I think a lot of the hardcore theories started to be developed moving into the latter parts of the 20th century and even into our current century, where you see a lot of applications. It wasn't just a matter of looking at things and thinking, well, how does this happen? How do these, what are we seeing? Why does it happen? And you have individuals like Russell and others, but Russell, I think, was a large proponent of this, trying to explain some of these observations, explain some of this data with some of his formulations. Science and religion. I mentioned he was a very religious individual, devout religious person. A couple of things too as we move throughout his career. He started writing for the Scientific American in 1900, a long time ago, and he did so for 43 years. Scientific American, I think, was actually first published in the middle part of the 19th century. Of course, it's still around today. Initially, he had a very short column, but I think the contributions to Scientific American over the year became more detailed and more complex. He was a liberal Christian thinker. He argued that science could strengthen religion by showing a unity of design and nature. And I think this was no doubt a principal tenet by which he lived, which he conducted his work both in his religious devotion and also his work, professional work. Say published over 200 papers, so his publication history is pretty extensive throughout his career. Legacy, quite a few things. He was a member of quite a few societies, a number of awards and medals throughout his career. I'll just let you peruse the list real good. You've seen a lot of these, particularly the National Academy of Sciences, the American Academy of Arts and Sciences. He did hold some offices where he was president of some of these organizations. Gold medal of the Royal Astronomical Society was a critical one. And I'm trying to remember, Doug, maybe you can help me with this. I know some of these prizes, some of these medals are probably some of the foremost in astronomy, are they not?
Yes.
Yeah.
I see
And so,
I see the Draper medal there. That's a big one.
okay. Yeah, I didn't research the medals, themselves, but it goes without saying, Russell had probably, with the exception of this one little disagreement he had with Kapotchkin, I don't think it was a big thing because most people didn't notice it. From the standpoint of his knowledge and his academic career, probably had one of the best standings in this country in astrophysics, astronomy, and science. He was a very personable person. I think he talked to a lot of people to conduct his work, and so collaboration, cooperation, I think, was every bit a part of his professional life as anything else was.
Take a
Okay,
look at
these
that.
are. Go ahead, Doug.
Go back one.
Yes, sir. Oops.
Interesting, at the bottom of this list, there's two entries. Foreign member of the Royal Society. That is something that is almost unheard of. That is very rare. And the honorary fellow of Royal Society of Edinburgh goes right along with that as being an extremely rare honor.
Are these both these societies just generic science societies, or are they specifically associated with physics or astronomy?
The Royal Society is a general science society of England, of course,
Right.
and the Royal Society of Edinburgh is the same. Interesting enough, you find very few Americans. They don't take in foreigners over there. The Royal Society is a very exclusive club. For him to get in there as a foreign member is a unique privilege.
Very good. Thanks for that ad. Appreciate it.
Notice it's a foreign member, though. I think they had a subcategory for foreign
So it is
members.
a unique privilege. There weren't many.
I agree with you. Yeah, there's very few outside of London that
Yeah.
or the UK that get allowed into that one.
These are some of the sources I have, and of course, as usual, thank you for your attention. Are there any other questions or comments?
Nice job.
Thank you.
Thank you.
He was an, it's been kind of interesting. I've been presenting these astronomers to you all over the past, couple of months, and I got to tell you, it's truly fascinating. Some of the things you learn. Okay, it was like when I did Halley. The only connection I had. Okay, there's the comet. In the case of Russell, it was just a diagram, but to find out that he was, like I say, probably one of the most preeminent astrophysicists in this country. Especially in the early to mid 20th century, was kind of interesting in and of itself and what the type of work that he was able to do and the positions that he held. So, thank you.
Thank you very much, Pete.
You're welcome, sir.
Can I get a quick mic check on myself too? My headset started going on the fritz.
Still loud and clear, sir.
Cool. And with that, I will take the share back from you and we will jump into
Okay.
our next topic when I put my slide back in order. There we go. Come on, Zoom. And everyone confirm they're seeing my screen?
Yeah.
Yes.
Cool. So as I mentioned at the start of this meeting, this is a representation with some updates to it of a presentation I gave way back in 2017. This is kind of a black hole primer, but I also spent a little bit of time talking about some of the math to it. Don't worry, it's not going to be too scary. We're going to briefly start with a history of black holes and some of the notable figures in their discovery, leading up to some of their initial acceptance into the public sphere. We'll briefly spend some time talking about some of the fundamental properties of black holes, and then we'll wrap up with some conversations about how black holes form and some of their different types. Our story begins way back in the 1780s with an astronomer by the name of John Michel. There's no T in his name. I had to check twice. Who was looking at what Newton had just published a couple of decades earlier, his Principia Mathematica, which basically set down the fundamental theories of gravity and invented calculus and a whole bunch of other things all at the same time. And Michel was intrigued by some of this, as well as Newton's other work with relation to light and optics. And he proposed out of nowhere the idea of a concept of dark stars, where a star's gravity was so intense that light just never left it. Reasoning what we now know to be a true statement that light can be slowed down by gravitational pull, which is kind of odd because I think at this point many people didn't still consider light to be its own thing, not necessarily thinking that it had mass, that it was still just sort of like this ether or substance that was different from regular matter. So making this kind of conclusion this early on was phenomenal. But with this initial proposition, that dark stars exist, he also proposed the initial strategy that we might use to detect them, namely that we would expect to see a star, an optical star that we do see, being having an orbit or being having its own properties impacted by an unseen companion, which is primarily how one way that we can predict now use to predict not predict to find black holes. Unfortunately for his work, it died mostly in obscurity in the 1780s, and we did kind of got kicked to the dust buckets of history for a couple hundred years. We don't really see much about this again until we get over to everyone's favorite physicist friend with funny hair, Albert Einstein, who, with his publishing of his general theory of relativity in 1915. Black holes were, still sort of this skeptical thing. Although they were sort of like this after effect of some of his more complicated equations, Einstein and one of his serial collaborators, Sir Arthur Eddington, kind of refused to accept that these might even exist. Even after Karl Schwarzschild, who we'll talk about here in a second, provided some of the first solutions to the Einstein's equations for general relativity, which defined the simple black hole, he was still just like, no, the universe can't allow these things to exist. We don't like infinities here. We then circle back again, the next making some minor advancements with the American Indian astrophysicist Subrahmanyan Chandrasekhar, who is the namesake of the Chandra X-ray Observatory. And Chandra provided a model, now known as the Chandrasekhar limit, that describes how a white dwarf star model on how a white dwarf star dies to determine if it would become a neutron star or a black hole. Note that kind of a little bit of misnomer there that white dwarfs stars die, but still making progress. And it doesn't get until 1967 where physicist John Wheeler officially coined the term of black holes, and then Stephen Hawking published his work that is was probably one of the hallmarks of his career, describing the.
Your mic is dropping. You're dropping in and out.
1 second. Can you hear me now?
Yeah.
If it persists again, I'm going to switch to a different mic and pause for a second. Where was I cutting out at? And I will restart.
You were right at. You just finished talking about Chandrasekhar.
Okay. So circling back, that black holes, as the term as we know it, was officially coined in 1967 by John Wheeler. And then we have the work from Stephen Hawking, which is, I believe, is the work that thrust him into the public sphere as a physicist and astrophysicist, was on describing the Hawking radiation mechanism, which we won't go into here. That's a little bit, takes a lot more work to explain than what I'll want to spend effort on. And we then circle to the very first detection of a black hole, which was identified as the X-ray object Cygnus X1. So general relativity being what it is, there are a lot of things that get a lot harder when you bring it in, but some things do get easier. Black holes are not one of those things that get easier. Black holes are weird, and probably besides the fact that people just are, when you talk to a layperson, you're just like, hey, why are these things? Black holes, they destroy everything. Nothing can escape them. But the reason that these are weird from an astronomical and from a science perspective is that they're the equations that describe them involve infinities all over the place. And despite the fact that gravity itself, excuse me, is one of the not is one of the is the weakest of the four fundamental forces between the strong nuclear force, the weak nuclear force, and electromagnetism and gravity. Gravity is the weakest out of all of those. I think it's like 6 orders of magnitude weaker than electromagnetism. It's able to create objects of this incredible weirdness. And so I can really say, but they're also responsible for shaping much of the universe. So gravity itself plays a big role of like, how can this seemingly insignificant force give rise to this endless maw? And because of their unique properties, we don't actually know, and probably, unless advances are made into gravitational wave astronomy, probably won't know whatever goes on inside of a black hole just because of the nature of nothing escapes. You can't recover any information or observations for something that traverses the event horizon of a black hole. We'll talk about what the event horizon is here in a bit. And, as I mentioned, you can't recover information, which is what's known as the information paradox of black holes, which is another thing that Stephen Hawking spent a lot of his time and research effort on as well. To kind of just illustrate in a very simplified manner what the deal here is, infinities, is imagine that this term is the bottom, is the radius of a star, and its radius is shrinking to 0. What happens here, for those that may somehow remember anything from high school calculus or entry-level calculus in college, is that the behavior of this is that this goes up to, that 1 over x is x goes to 0. This goes up to infinity. It doesn't devolve into something undefined. So it's similar to what happens in a black hole, and that is its radius shrinks to 0. Other things get really, really weird. Namely, its gravitational pull gets to infinity. And the only reason that this doesn't destroy the universe is because gravity can only act within a range of itself. So that's a very jumbled explanation of why infinity plays such an important role here in understanding black holes. Reading this one out, just because I find it funny and true to a lot of science, especially when we get into things with dark matter and black holes, is yes, everybody has already had the idea. Maybe there is no dark matter, that gravity just works differently on large scales. It sounds good, but it doesn't really fit the data. So, so a black hole itself is kind of sort of hinted at here is a vast quantity of matter that's been compressed from a three-dimensional sphere, a star, down into a one-dimensional point. And so if you were to just take a sphere and crumple up into a ball in your hands continuously until you could just drop it onto a piece of paper like a snowflake, that would be a semi-reasonable interpretation of what happened to a black hole. Their gravitational field is so strong that their escape velocity, which means that how fast you need to be going in order to leave the vicinity of a black hole, is equal to the speed of light, which is why nothing can escape them. Black holes that we most typically associate with are created by the deaths of stars that are larger than 20 solar masses, which also means that our sun will not become a black hole. It'll just become a white dwarf. And they are not directly observable. Even the closest black holes to Earth, we can't actually, ignoring supermassive black holes, but stellar mass black holes, you can't directly look at them. It's not possible to see the singularity, which is that point that sits inside the black hole, but we can see their event horizon, like we have with the Event Horizon Telescope, which is a separation here between imaging. It's like imaging Earth's atmosphere without imaging the surface of the Earth itself is the closest explanation, which is why sometimes people are like, well, what's the deal here? To, um, so illustrating some of the more, going back to the properties of black holes and the escape velocity. And this is a thought experiment that was originally proposed by a physicist named William Unruh, who asked the audience to imagine a fish screaming as it plunges over a waterfall into a lake or a trough below. The water itself is falling so fast in this fictitious waterfall that it exceeds the speed of sound. This water is falling faster than the speed of sound once you get somewhere closer to the bottom. And once the fish has progressed past this point where the water is moving faster than the speed of sound, you can no longer hear the fish scream. Yeah, this is sort of a rough analogy of what's going on as you approach a black hole. With a black hole itself, we've mentioned a couple of different components about them. The main thing that one of one component is the singularity itself, which is this one-dimensional point that contains all of its mass. This is, the physical manifestation of the black hole. And we currently believe that, all singularities of a black hole will have an event horizon. I won't really get into some of this. That portion gets into some deep physics. But a naked singularity is essentially a singularity that does not have a black hole. And we think that the fundamental properties of our own universe prohibit a naked singularity. So we will always have an event horizon associated with a black hole, to our knowledge. The event horizon is commonly depicted as the point of no return. It's this visible boundary that you see whenever somebody shows you a picture or a graphic representation of a black hole. What you are seeing is the event horizon itself, essentially the atmosphere of the black hole, and it is the point where the gravitational acceleration around the black hole itself is at the speed of light, which turns it into this pitch black sphere. And many people commonly associate the event horizon as being the black hole itself, where that's not. It's just it's just the most visible component as a result of this gravitational field of the singularity. This is sort of the more interesting depiction I was trying to find of illustrating, how the absence of light around an object changes its appearance. And this is just the same sculpture, but on the right, it's covered with a pigment known as vantablack, which absorbs 99.99999% of light that hits it, much like how a black hole's event horizon would appear. It's just very black. Even on computer monitors, it would be hard to fully depict. It's just the blackness of it. The last component of a black hole is what's known as the accretion disk. This is just a spinning disk of matter that is orbiting or infalling into a black hole. It's going to eventually move past the event horizon and fall into the singularity. And this material is typically coming from the accretion is typically formed by a material that a black hole will steal off of a orbiting companion star, or perhaps from a nebula that the black hole is residing in, if it is inside of a nebula. And what happens to this matter is, as the black hole starts to pull it in, the speed at which it starts spinning around the event horizon increases its temperature dramatically, to the point that the material will start emitting X-rays and gamma rays, which is how we originally detected the first black hole of Cygnus X1. We were looking at X-ray and gamma ray emissions from the accretion disk around the black hole. And if you have seen the movie Interstellar or the Event Horizon telescope pictures, you'll see that there is some weird effects going on to the event horizon, to the accretion disk, and that gravitational lensing, which is coming from general relativity, that the gravity of massive objects can distort the appearance of light that travels around the object. The same thing happens to the accretion disk of a black hole, in that the accretion disk on the far side, the light from the illuminated by this accretion disk is reflected around the black hole itself, which gives it this weird two-dimensional disk shape like we see here. So in this case, the accretion disk is on the plane directly edge onto us, but the top and bottom of the black hole are simply bending the light of the accretion disk on the opposite side, which gives it this funky appearance. So circling back to some of the more interesting physics on this, Carl Schwarzschild, who I mentioned as the person who provided one of the first closed solutions to Einstein's general relativity, calculated what we now know as the Schwarzschild radius, while serving as an artilleryman on the eastern front of Germany during World War I. Between not getting shot at or shelled at by the Russians, he was, solving math equations. And this equation, this radius that he could define, is the radius of a sphere, where if all mass of that object is within that sphere, the escape velocity equals the speed of light. And if you have any object whose physical radius is smaller than its Schwarzschild radius, it's a black hole. What's interesting about this is that it assumes two things, that the object itself is not rotating and the object itself is electronically neutral, which is interesting to think that a black hole can spin, which and that a black hole can have an electric charge. But uh, we know that to a certain extent that black holes themselves can be disturbed by gravity of their neighbors. So the event horizon itself, like the surface of the Earth, won't maintain a perfect sphere. It'll have a little bit of a bulge to it if it's being influenced by a nearby companion star or a nearby companion black hole. There's another set of equations that you need to use if you wanted to deal with these objects. We won't get into them, but if you're interested, they're known as the Kerr-Newman metrics. And at the lower right here, we have his equation, the Schwarzschild radius, which is 2 times the mass of the object times the gravitational constant divided by the speed of light squared. So a very simple and elegant equation to describe, hey, if this object, if the sun were to turn into a black hole, how big would its event horizon be? Is essentially what this is describing. This here is a question that was asked to a series that I follow, which is asking, what happens if you were to replace the moon with an equivalently massed black hole, and what would this lunar black hole look like? Convenient which answer is that a black hole that has the mass of the moon would have an event horizon that's the size of a grain of sand. So the gravitational constant G is important in Schwarzschild's equation, in the Schwarzschild radius, in order to determine uh, what uh, what the radius of a black hole's event horizon is. But there's an interesting note I found recently while looking at this, and the gravitational constant was first calculated to within 1% of its true value that we know today by Henry Cavendish in 1798. And the experimental setup that Cavendish used, which is this funky apparatus used on the right, was originally devised by John Michel, who originally proposed dark stars. But unfortunately, Michel died before he could actually attempt the experiment with this. And over time, this plans for this apparatus passed to Francis John Hyde Wollaston, who then eventually sold it to Cavendish. Cavendish to perform the experiment. So interesting note here, circling back to the first discovery of black hole and some of the fundamental constants in the universe that we need to know that are important to a lot of astrophysics today. The other fundamental property that I've mentioned is, hinted at with what comes from Chandrasekhar, and it was, originally coming out him studying white dwarfs and how white dwarfs evolve and die. And the Chandrasekhar limit was originally ignored, again, in this early time, because it had to, in order for this limit to be applicable to universe, it required the existence of black holes, which Einstein, Newton, not Einstein, Eddington, and several others, like, we don't think these things exist. So it was kicked to the curb for a long time, in part driven by Arthur Eddington and Arthur Eddington's influence on this particular field of research, and Einstein's as well. What the main thing that this limit defines is the maximum stable mass of a white dwarf star. And if a white dwarf star exceeds this, it'll either collapse into a black hole or evolve into a neutron star, depending on some circumstances. So this is just simply, there's beyond a very massive star dying, there are other ways for a black hole to be created besides a supernova. And you just have to have a white dwarf gather in a lot of mass. The other fundamental property that coins into the relates to some things important with the accretion disk is what's known as the Eddington luminosity. And this was originally proposed by Sir Arthur Eddington, who at the time was interested in studying the luminosity of very massive stars. He wanted to understand what is the largest a star could possibly become in our universe. And what he found in this is that there's this balancing act between gravity sucking in material and the radiation pressure released by the heat of this material as it condenses and grows in pressure, like in a star, it's going to start generating X-rays, gamma rays, so on. That this radiation itself is a pressure force that will push material away as it's being drawn in. So it's a feedback loop around how a star might quickly gather material. And while this was originally proposed for how quick limit the formation of supermassive stars, which we now know that think that the upper bound limit of stars in our universe is around 200 solar masses. This also comes into play for black holes, and it defines how quickly a black hole can consume material as it falls from the accretion disk to the event horizon and into the singularity. And we're getting close to the end here with finishing up with the different types of supernovas, not supernovas, black holes, getting terms easier. Starting with what probably is the more interesting topic today in modern astrophysics of supermassive black holes. These were first hypothesized around the time of the first detection of a black hole in 1971. And we detected our first supermassive black hole as Sagittarius A 3 years after we detected our first stellar mass black hole. Currently, we think that these supermassive black holes reside in the center of all galaxies. And as we're finding out with James Webb, that these galaxies were first forming within the first 300 billion years of the Big Bang. And so we were having potentially these supermassive black holes form very, very early in the universe. And we're still kind of at a puzzle as to some of the fundamental mechanics of how would a supermassive black hole gain enough material in it this early in the universe's history to get the mass that it has. So circling back to the Eddington luminosity here, how we need to get, hundreds of thousands to millions of solar masses of material could turn into a black hole within, potential within at most 300 million years, which is, and we're not quite sure exactly how that happened. It could be that, early in the universe that Eddington luminosity just didn't apply because there was some different physics going on in the primordial soup of the universe, or any number of other reasons that I can't think of off the top of my head. Supermassive black holes typically have a range, as I mentioned, of 100,000 solar masses up to billions of solar masses. And by a quirk of explanation, it turns out that you can interpret these supermassive black holes of having a density that is less than water. I'll explain that with a visual here in the next slide. So when we measure density of an object, we typically say this thing has a surface. And what is or a volume? A surface that defines the volume of the object. And when you say, hey, the surface of our object of a black hole is the event horizon, and you say, well, what's the mass of all the material from the event horizon in? It turns out that supermassive black holes, because of their size and the size of their event horizon, the gravity that you would feel across the event horizon feels like just slipping into water by one analysis. not quite sure I'm explaining that correctly. So feel free to ask questions about this uh, when we get near here to the end. It is kind of one of those confusing things, and you have to sit there and toy with it in your head a couple of times to be like, okay, I see how this is. It's kind of a play on a difference of interpretation, really. And this is an example of a binary supermassive black hole. There are two in this image, both with jets. This is found in the uh, object NGC 1128 in the constellation Cetus. And I did not see. I think this is a Hubble or a VLT image. Stepping down from zero-massive black holes, we have intermediate mass black holes. These still in the gap of 100 solar masses to 100,000 solar masses. And we haven't still have any real strong confirmed detections of intermediate mass black holes. We have a lot of candidates, but nothing's been fully confirmed that, yes, this is an intermediate mass black hole. We think that these objects are formed through the merger of black holes or black holes and neutron stars, which we can see if we've following some of the gravitational wave sources that have come out from the LIGO and Virgo experiments, which are gravitational wave detectors, and we can see them slowly building up. One possible candidate that we have for an object near us that has an intermediate mass black hole is the globular cluster NGC 104 and also the globular cluster Omega Centauri is also thought to house a intermediate mass black hole, which part of it also being that Omega Centauri is also believed to have been the core of a dwarf galaxy that has been merged with the Milky Way. And then as our final step, we get down into stellar mass black holes. As I mentioned, these were first detected in 1970. And they are formed by the death of a massive star through a couple of different mechanisms. And they range in mass from 5 to 100 solar masses. And the theoretical minimum mass for a stable black hole is around 3 solar masses. You may recall earlier that I showed a figure from the Chandrasekhar limit about the maximum size of a maximum mass of a white dwarf, excuse me, of being around 1.4 solar masses. So what this is saying here is that if a black hole is formed from a white dwarf, so it falls into this 1.5 to 3 solar mass gap, that black hole isn't stable. And I wasn't quite able to figure out what exactly that means in terms of how that black hole evolves. Will it evaporate? Will it dissipate? Couldn't find anything definitive there. So one way that we can get a supernova can form a black hole. A black hole can form besides the supernova, excuse me, is what's known as the neutron star pair, which this occurs in a system with one or more neutron stars. And a massive star will undergo core collapse into a neutron star. So this is a star that's not quite 10 solar masses, so it won't go directly into a black hole. And the recently formed neutron star will start siphoning material from one or more of its companion stars. And when the neutron star exceeds 3 solar masses, it will collapse directly into a black hole. We think that this mechanism is one primary source for what we observe as gamma ray bursts. The other route, which is the most common one that we see in the universe, occurs for what's known as the core collapse process. This occurs in stars that are between 10 solar masses and 100 solar masses. And the star will shed its outer layers before its core, which at the time of its death may mostly be consisted of iron and other less heavy elements. And core will collapse directly into a black hole. The next route is, well, not really a route. It's really more of uh, a failed black hole, but it's uh, an interesting point on the scale where stars that are heavier than 130 solar masses uh, will disappear. They won't have a supernova, they just vanish from the sky. And what happens is that the star has so much mass that some of the photons that it produces are converted directly into matter. As, a, as this happens, this matter takes away energy from the star. It gives it less less energy to help resist the force of gravity from collapsing the star itself. So this ejected off as solar wind particles in very rapid amounts, very vast amounts, excuse me. And at a certain point, the whole star just disappears. It doesn't form a black hole; it just vanishes. But in between this, oh, sorry, this is the one. This is what an image showing one possible candidate of a star that has potentially undergone a direct collapse. It just disappears off of this image between 2007 and 2015. There's no sign of a supernova in this region. There's no other gas or brightness in it. Just gone. Um, and but between this, we left one side of core collapse of copying at 100 solar masses. Then we had this direct collapse topping at 130 solar masses, and we have this gap in between this. So stars that are in this island of being between 100 and 130 solar masses also go through this light to matter conversion process, but at lower volumes, lower intensities. And during this process, as light is getting converted into matter and ejected from the star, the core itself will undergo one or more partial collapses. So it'll try to crush into itself before rebounding a little bit and throwing off the outer one more layer, one extra shell of the outer layer of this star. And during this process of repeated, ejecting light, partial collapse, ejecting light, partial collapse, you can lose up to 10 solar masses of this star of total material. And eventually this ejection process will repeat enough that the star can finally undergo core collapse into a regular black hole. Well, undergo the core collapse process of black hole formation. We haven't observed any supernovas that would be signatures of this process, but we think that the Eta Carinae supernova remnant is one possible candidate for this type of process. And I don't believe this is referring to the star that formed the homunculus nebula. I think it's referring to something else, but I can't remember now off the top of my head. And that was a big information dump. I'm open for questions. And I see Doug tilting his head back and forth. Something's wrong here.
I ain't gonna say anything.
Hey, Connor, I do have a question. I remember reading, well, actually, it was recently, and I can't remember where I saw it, but talking about Hawking radiation, it's one of those things that comes out of a black hole where stuff normally doesn't, correct?
It's yes, but no. It's a
Okay,
very weird thing
I'll
to.
accept that. I'll accept that. But generally, that's indicative. And the term I saw being used, not so much the death of a black hole, but I think the term they used was was evaporation of a black hole.
That's
Yep.
a better way to describe it.
But eventually it will evaporate away the entire black
Yeah.
hole.
I'm sorry, Doug. You said that was the better way to describe it?
Yeah,
Okay.
Just I give you the 30-second spiel on Hawking radiation, just so you know what it is. Um, E equals mc squared, right, is the
Yeah,
rest energy of mass. Okay. But part of the theory of relativity that came up with that also says that you can have spontaneous formation of a particle and an antiparticle in empty space.
right.
Okay, well, so what Hawking radiation is imagine this set of particles forming right at the event horizon.
Roger
One
that.
of
That's the
them,
way. That's what I saw. Yes.
one of them goes into the black hole, the other one goes out. By the conservation of energy and conservation of momentum, the black hole has to shrink a little bit whenever that extra particle disappears.
Thank you. Now I recall. That's the way it was explained. Yes. In fact, I think there was. I know what it was. It was a recent article. I think it was in Astronomy magazine. They have an article on black holes, and I think that was basically one of the paragraphs in there. Thank you.
Any other questions or comments?
Yeah, Connor, I got a couple. First, I'd like to talk about the history. John Michel,
Hmm.
um, I guess he called it a dark star. Uh, so he must have figured out that um, you know, like a binary star system or something that if you can't see one, that's a dark star. So I guess my question is, did he or they think about it as being a gravitational thing that pulled photons in, uh, or did they just say, or were they just saying, "Oh, we see the effect of it, but we don't see it, so it just must be a dark star." Did they actually understand the the concept of the gravitational pull of the gravity on light?
That itself is unclear to me, just because the resources that I had at my disposal that would talk about him didn't really go into that level of depth, and I didn't
Yeah,
see the actual any publications that he didn't find any publications that he wrote that would have described what he was reporting here. So I can't answer your question. I
yeah.
do not.
Well, that's fine.
One additional comment, they did have part of it wrong because they didn't understand, uh, they didn't know anything about relativity at the time of John Michel. Um, they didn't know that light had a constant velocity. So his original thing about light slowing down by gravitational pull, that's not correct, obviously. That's not what's happening.
That's just my phrasing on this slide,
Yes, I
Doug.
know, but that they didn't have any understanding of light having constant velocity. In fact, back then they assumed it didn't.
Well, I guess this is the first I've heard of that long ago. They understood. I mean, I guess they would have been Newtonian physics type people at the time, so they
Right.
must have understood, you know, something about gravity, and that if there's enough mass, that there could be enough gravity. So maybe they didn't see it as, I mean, uh, as relativity, but uh, I was just wondering if they had that amount of understanding, or if it was just a dark, that like we think of dark matter today.
Yeah,
So,
I don't know how far they made with
yeah.
that conclusion.
Okay. Now I have another one for you. So it's been, half a century since I did college calculus, and took limits of things to zero, to end up with the concept of dividing by zero being infinity, or a singularity, or asymptotically approaching such a thing. It's just kind of always never really sat right with me that you would have to require a singularity in order to have a black hole. It seems to me, if three solar masses is enough to create a black hole, is that enough to create a singularity? That it seems like
Yes.
that
A
wouldn't
black
really.
hole, a black hole and a singularity are the same thing.
Well, I guess I always thought of the black hole more as a concept of
Event horizon.
the event horizon, because they always say, well, it's, light can't escape from it. And
Yeah.
where does that happen? That happens at the event horizon.
Right.
So to me, the black hole is the event horizon.
The event horizon is just a calculation that shows that if you if you go inside that event horizon, the escape velocity to get out is greater than the speed of light, and we
Mhm.
can't do that. So that's why the event horizon is the boundary. The actual black hole itself is the singularity.
Which goes back to
Okay.
why I was saying, if you recall this diagram when I was talking about the density of a black
Yeah.
hole, why it started this whole, wait a second, I need to think about this some, because most people like you assume that the event horizon is the black hole. It's really just a manifestation of the singularity that is the black hole itself.
Mhm.
So Tom, what happens when you reach that magic three mass solar mass limit or whatever limit you want to talk about that collapses, you get that much mass in a very small area where it collapses down to
Mhm.
a black hole, is that you've overcome all of the fundamental forces. The gravity now is stronger than the strong nuclear force. It's stronger than the weak nuclear force. It's stronger than the electromagnetic
Point.
force. Nothing stops the gravity from collapsing the mass down anymore. And it just crunches out of existence, essentially, down to zero volume. We honestly don't know if that's actually
Right.
what happens, but in theory, that's what happens. All the mass gets concentrated in a single point that has zero volume. And that's where you get the infinities coming out of, because now you've got a mass, a huge mass, 3, 5, 10 solar masses, whatever, in a single point. Volume is zero. So what's your density? It's the mass
Mhm.
divided by the volume. Well, your volume is zero. So here
Right.
you are dividing by zero. There's where you start getting all the infinities in the equations.
Right. Well, it just always kind of felt to me like somebody looked at the math and said, "Oh, gee, what would happen if we actually did go to zero in the denominator?"
The math falls
And
apart.
then fit the concept to that. It
Yeah.
just,
That's what happened with the Schwarzschild equations. That's how he arrived there.
yeah.
I wanted to enter just my side note because I remember you had on one of the slides, how would you die if you fell into a black hole or something like that on one of the slides? I always found that interesting because that goes back to the thing about the density being like water. If it's a little black hole, like from just a single star, okay, if you were to cross the event horizon and pass into that black hole, you'd get ripped to pieces by the tidal forces because the gravitational force difference between your toes and your head would be enormous and you'd literally get torn to pieces. But if you fell into one of these supermassive black holes that's at the middle of a galaxy, you wouldn't even feel it. You wouldn't notice it. You'd pass through the event horizon and not know it, but yet you could never get out. If you were in a spacecraft and flew in to one of these massive black holes, your spacecraft would perform normally. All the systems inside the spacecraft would work just fine, but you could never get out.
Unless you are Matthew McConaughey.
It's troublesome for people to understand how all of that mass can be down to one point.
Yeah.
And yet at the same time, the Big Bang was a point that grew to the universe. We have no problem with that part.
Yeah. Well, this is, I mean, that's one of the reasons Eddington and Einstein didn't want to believe in these things because they couldn't comprehend or they didn't want to comprehend the idea that everything got down to a singularity, to a single point in space, and all those weird things happened. They just didn't want that coming out of their beautiful equations for relativity. They didn't want it coming out of that.
Would also add that at this point, when general relativity and the Schwarzschild equations were first proposed, is they didn't have a concept of the Big Bang yet. They still thought the universe was eternal. The Big Bang didn't come about as a standalone theory for another
Yeah,
30 years and accepted for another 10
Eddington
after that.
Eddington was a strong believer in the steady state universe.
Hey, Connor, another question.
Mhm.
As far as I know, with respect to the theories associated with black holes, the inverse square law with respect to gravity still applies, yes?
Yes,
Yes.
All the way to singularity or just to event horizon, or doesn't it make a difference?
always singularity.
Okay, thank you.
That's why, like I said, you wouldn't notice it if you flew into a really big supermassive black hole, because the tidal forces are not going to, the gravity doesn't change that much
All
from
right,
the bottom of your feet to the top of your head, because the supermassive black hole is so large. But on the smaller black holes, the tidal forces are going to be much different.
get it. Thank you.
And let me double check the chat because I see that we have some comments there. No, okay, no questions in the chat. So that was a bit of an information dump and some good questions and conversation. And with that, I'm going to go ahead and end the share there. And that's all I had for tonight. So I will let everybody go. Thank you for listening to the info dump. It is still, I tried my best. It's still a complicated topic to try to explain without a lot more time and a lot more figures. So,
Thank you,
and with
Carter.
that, I will see everybody
All
next
right.
time.
Good night.
Good night.